Okay, this is the second video that you guys can watch while I'm away next week. We're going to dive a little bit deeper into Chapter 8 so that we'll get most of the work done because you're going to watch these, I'm sure, several times and learn all about the topics in Chapter 8. So when we meet on Thursday, we can hit the ground running. This video is going to cover electron configurations of ions, and we're going to review a little bit of work around quantum numbers just to tie it all together. So we know how to write electron configurations. I think everyone's doing pretty well with that. But now we're going to have to tie it into the formation of ions. And that's going to involve a little bit of vocabulary and a new skill. And then, as I said, we'll review quantum numbers in context of all of that. Okay, so what are ions again? I'm sure many of you could use a refresher. We haven't really talked about ions since chapter 3. And so ions are atoms that have either gained an electron or electrons or lost an electron or electrons, right? So it's the picking up or the letting go of electrons. Electrons, of course, carry a negative charge. So when we gain an electron, we've gained a negative charge. So we call that the anion. If we lose an electron, we've lost a negative charge. And so we carry a positive charge. So anions are negative, cations are positive. We could gain an electron or lose an electron. And we're going to talk about that with respect to the periodic table and where these ions are located. If we think about sodium, sodium we know lives in group 1 metals. All group 1 metals carry a positive 1 charge. So sodium is going to lose an electron. Now that we know where electrons live, right, we know what shell they're in, we know what subshell they're in, which orbital they occupy, we can talk about sodium losing an electron in much more detail than we could have on the first day of class, right? So now we could think about how sodium forms this positive charge. If I were to write the electron configuration for sodium, I would start at hydrogen and go from left to right, row to row. So we fill up 1s2, 2s2, 2p6, and 3s1. If I were to draw the orbital box diagram, like we learned in the video that came just before this one, I would put one box to reflect the s orbital, one box to reflect the s orbital in the second energy level. For the p orbitals, I'd do 3 boxes for the 3 orbitals, the x, y, and z orientation of the p orbital. And then for 3s, I'd get another little box for 1 orbital in the s. So I could go ahead and fill those in, right? We used all those rules, Hund's rule, Pauli exclusion, Aufbau, and I would start with my low energy, and I would make sure that they have opposite spin, filling my low energy shells in my high energy. When I got to 2p, I could use Hund's rule. Make sure everybody gets their up electron before anybody gets their down electron. So he's full. And there's my 3s electron. Okay, I'm going to introduce a little language now, and then we'll follow up with it later. This electron is in the outermost energy shell. This guy has electrons in the first, and the second, and the third energy shell. This is his largest outermost energy shell. And so any electrons in n equals 3, we call those valence electrons. Valence just means the outermost. So we could have a valence shell, or we could have valence electrons. Those are the electrons in the outermost shell. So we'll come back to that. Now, if I wanted to form Na plus, this tells me that we lost 1 electron. It's not just any old electron. When ions are formed, ions gain or lose valence electrons. They're only going to lose their most reactive electrons. So we're going to go to the outermost energy shell. We're going to see that 3 is the biggest number, 1, 2, 3. He's the outermost. There's the electron that sodium will lose. So in order to become sodium plus 1, he's going to let go of his 3s electron. When he does that, he will lose the 3s shell entirely, and he will just have 1 and 2 as his energy shells. So if we were to draw his orbital box diagram after he lost this electron, that electron goes away when he forms his ion, and I'll see that I have 1 s2, 2 s2, and now my 2p6 will be full. Okay? Now, in the first video, we said that if we had an orbital box diagram with unpaired electrons, we called that magnetic, which we also could call paramagnetic. Those were the same words. If I look down here at sodium ion, I have an up paired with a down, an up paired with a down, all the way down the line. There are no unpaired electrons. This is not magnetic. We call not magnetic, for reasons that are very confusing, we call that diamagnetic. Paramagnetic means magnetic, diamagnetic means not magnetic. But this is how we could go about understanding how the orbital box diagram and the electron configuration can explain how we form ions in a really detailed way, because now we know where every electron lives. Now, when sodium, who has 11 electrons when it's an atom, forms an ion, it ends up having 10 electrons. 10 electrons happens to be how many electrons the noble gas neon has. Ions typically form so that they can feel like noble gases. They don't become noble gases, but they have electron configurations matching those of noble gases. So ions typically, not always, but typically form to gain electron configurations similar to those of noble gases. So, when sodium went from having 11 electrons to having just 10, it became isoelectric with neon. Iso means same. Electric is short for electron configuration. So sodium plus has the same electron configuration as neon. Sodium did not become neon. That's an issue of protons. But sodium did gain an electron configuration similar to neon, so he's sort of faking it. But neon, being a noble gas, is very stable. And so sodium plus is also very stable because it has the same electron configuration. So we'll talk more about that when we join up in class on Thursday. But that's how we can combine our ability to write electron configurations and orbital box diagrams to understanding what ions really mean. Okay, let's think a little bit more about valence. I just want to make sure that I explain this in as many ways as possible. How many valence electrons atoms have is very important to how they react. So, if we were to look at something that had n equals to 1, we know that the first energy level can only hold 2 electrons. When n equals 2, we can get s's, right? And we can get p's. And that's 2 plus 6. And that's where they're getting this 8. Likewise, when n equals 3, on first pass, we get s and p. Okay, so we get 2 plus 6. And that's where they're getting this 8 again. Now, we know that when n equals 3, we also have some d electrons, but they're down here. And for the purpose of valence electrons, we're really only interested in s plus p. We do not really consider the d electrons. And we could talk more about that when we're together in person again. But we're really thinking about how many s electrons are there and how many p electrons are there in the outermost shell. So the valence electrons come from this outermost shell. Remember, valence, I said on the last slide, is equal to outermost or biggest. The one on the outside of the atom. So to find out how many valence electrons a particular atom has, we have to find its biggest energy level. So let's say I wanted to find this guy right here, whatever atom this might be. I would find out what row he's in. He's in 1, 2, 3, 4, 5, right? So his valence shell is 5, and then I want to figure out how many electrons, right, he has when n is equal to 5. To find valence, I'm just going to add s and p. So I'm going to count 1, 2. I'm going to skip my d's. So 1, 2, 3, 4, 5, 6. This guy has a valence shell of 5, and it contains 6 electrons. Any atom with 6 electrons in its valence shell reacts in very similar ways chemically, right? So we could also think about valence shells as going down these groups. This is why we have alkali metals behaving in very similar ways. It's why they get stacked up on top of each other. Lithium, potassium, oops, that's sodium, potassium, all of these guys in group 1 behave very similarly because they're all trying to lose that 1 electron in their s subshell. So everybody in this column has 1 valence shell, or I'm sorry, valence electron. Everybody in this column has 2 valence electrons. Again, we don't really talk about these guys. They're not doing us any good right now when we talk about valence for reasons that are sort of complicated. When we get over here, we have 3 valence electrons, and then anybody here has 4. S's plus P's. So that means the number can range from 1 to 8. If I ever ask you, and in chapter 9 I will, again and again and again, I will ask you how many valence electrons does that atom have? And you will find the atom, and you will count from the S's to the P's in the row that that atom lives. So this atom would have 5 because we have 1, 2, 3, 4, 5. So he has 5 valence. We'll practice on a real periodic table, but the ability to count up how many valence electrons there are is going to be really important in chapter 9. So I'm just taking a moment here to tell you about it in a video so you can come back and watch it later if you need to. So if we were to look at this periodic table of element and I wanted to find out how many valence electrons potassium, nope, I'm circling phosphorus right now, phosphorus has. Phosphorus, I could do his entire electron configuration, but if I just look at his outermost shell, that's 1, 2, 3. So here's his outermost shell because he lives in the 3rd row, and I just have to count till I get to him. 1, 2, 3, 4, 5. So phosphorus has 5 valence electrons. That's going to tell us about how he wants to react, right? If he has 5 valence electrons and he wants to form an ion in order to feel like a noble gas, then he needs to pick up 1, 2, 3 electrons. He has 15 electrons total, and he wants 18. But also he has 5 valence electrons, and we know that in the valence shell, for it to be full, S plus P, 2 plus 6, he wants 8 valence electrons. We call 8 the octet. We'll talk about that more in chapter 9. Okay, so phosphorus has 5 valence electrons. Silica would have 4. 1, 2, 3, 4. So we'll talk about that more, but I'm planting the seed now. We'll come back to it when we're together on Thursday. Okay, so let's practice more ions. Back to figuring out what the ionic charge is and how we can write electron configurations for ions. Let's look at sulfur, right? So we're going to look at sulfur. Sulfur, according to this periodic table, likes to form a -2 charge. Okay? Now you knew these back in chapter 3. You had to know them. It's +1, +2, +3, plus or minus 4. These guys are a bit of a mess. And then -3, -2, -1. So that should be a review for you guys. But sulfur likes to form a -2 ion. If sulfur forms a -2 ion, that means it picks up 2 electrons. It adds 2 electrons. So sulfur itself has 16, right? Sulfur has 16 electrons. If it adds 2 more, it's going to turn into argon. Argon has 18. So he's turning in his electron configuration from 16 electrons to 18. Sulfur does not become argon. Sulfur just develops an electron configuration similar to that of argon. So we say that the sulfur anion is isoelectric, right? Same electrons as argon. Now, if I want to write his electron configuration, I can just think about writing sulfur's electron configuration as I would to write argon's electron configuration, right? Because I'm suggesting that they have the same number of electrons. So if I'm trying to write argon's electron configuration, I could just start in my abbreviated form, right? In my abbreviated form, I start at the noble gas that happens just before sulfur 2- or argon, and I write neon. That places 10 of my electrons, right? So I've just talked about 1s2, 2s2, 2p6. I start here at 3s2. Oops, I don't need equal signs, but I can't make them go away. 3s2. After I talk about 3s2, I go over here. I bump into 3p, and I have 1, 2, 3, 4. Then I get 2 more because I'm going all the way to argon for the ion. So I have 4, 5, 6. 3p6. So this would be the electron configuration for sulfur 2-. The electron configuration for sulfur 2- is equal to the electron configuration for argon. So that's why I had to list all of the electrons all the way to argon, because he picked up 1, 2 extra electrons to become isoelectric to argon. Let's see if we can practice another one. Oh, I drew some boxes here so you could fill those in too. So we have 1, 2, 3, 4. Hund's rule says we fill them all going up. We fill them all going down. This is neon. When I write neon, I'm writing 1s2, 2s2, 2p6. Now I can start filling in 1, 2, and now I can fill up the entirety of 3p, and that is the electron configuration and the orbital box diagram for sulfur 2-. You're going to want to make sure you can do these on your own. Try them, practice, come back to the video, whatever you need to do. I know I'm going kind of fast, although some of you may find this actually quite slow and boring, but here we are. So use these as examples, how we can decide what sulfur or any other atom turns into when it makes an ion. Okay, let's do magnesium. So if I want to use magnesium, magnesium's here. This is a reminder that it forms a +2 ion, but this you'll have to memorize. So if magnesium forms a +2 ion, it loses 2 electrons. If it loses 2 electrons, it's sort of going backwards twice. It's going backwards to sodium, and then sodium's going backwards to neon. So magnesium 2+ is isoelectric to neon. So if I want to write the electron configuration for magnesium 2+, I really have to write the electron configuration for neon. These guys have equal or the same electron configuration, isoelectric. So neon's electron configuration is 1s2, 2s2, 2p6. Right? I imagine helium lives here, and I say I've got 1s2, 2s2, and then I go all the way over to neon, and that gives me 2p6. I could draw orbital box diagrams, but I think you guys probably have that by now. You could practice it and see how it goes, but this is the electron configuration for magnesium 2+. Nitrogen -3. The -3 means he gains 3 electrons. Magnesium 2+ has 10 electrons. Convince yourself of that. Check out magnesium. Take away 2. He has 10 electrons. Nitrogen has 7 electrons originally and gains 3. He is also in an ionic form holding on to 10 electrons. Nitrogen to the with a -3 charge and magnesium with a +2 charge, they are both isoelectric to neon. So if I wanted to write the electron configuration for N3-, it happens to be the exact same electron configuration as magnesium 2+. These are not the same elements or ions, it's just that they own and control the same configuration of electrons. So there we've written the electron configuration for the nitride ion. Bring any questions you have to tutoring or class. Feel free to shoot me an email and let me know how it's going. We can review all of this on Thursday. So let's practice all of this together and do a little quantum number review. If I wanted to write the electron configuration for bromine, I don't know, he didn't pop up there, this would be his electron configuration. We've seen it before in an earlier slide, I think. And so now we can also look at bromine, the anion. If he has a -1, then he added 1 electron, right? He picked up an electron. He went from 4p5 to 4p6. So if I wanted to write the orbital box diagram for the bromine negative ion, I could have 4s, 3d, and 4p. This guy popped up over here. This is just the abbreviated one if you wanted to see it. So everything up to 4. Oops, went too far. Everything up to 4 is argon. So all of this stuff is there when we say argon. Right? So we can lump all that stuff in by drawing argon with his brackets. This is the abbreviated form. And then we can go 4s2, 3d10, 4p5. Okay, but back down here to the ion, we've added 1 electron, taking him from 4p5 to 4p6. I could draw his orbital box diagram. Everybody would be full because he's made an ion and ions form to mimic the noble gases. So he could be full. I could follow Hund's rule. Place all these electrons, go to 4p6, right? So there's that last electron that I just placed. Now, just throwing it out there to review, everybody has an up and a down electron. Bromine negative, I would call diamagnetic. I have to look at the orbital box diagram to learn about the magnetism. Okay, so this is the last electron I placed. This is the electron right here that turned bromine into the bromine anion. If I go up here and look at these boxes, I don't think I animated these boxes, so I might draw them myself. I hope that's true. If I were to fill these guys in, these are all full. And I want to place 4p5. This guy would go 1, 2, 3, 4, 5. Do you see that guy's missing? This is the electron that turned bromine into bromine negative. Let's write the 4 quantum numbers for that electron. So the electron that turned Br into Br minus, we could come up with his address. We're going to need 4 numbers. We're going to need the principal energy number, the angular momentum number, right? The magnetic, and the spin. The first number that we want is the floor that electron is on. We know that we put that electron into the 4th energy shell because it has a 4 in front of it. So N is equal to 4. L tells me about my subshell. Am I in S, P, D, or F? Right? That tells me if I'm in S, P, D, or F. I'm in P. So I placed that electron into a P subshell. So P has an L of 1. Remember, it goes 0, 1, 2, and 3. So I've placed it into L equals 1. Now I need the M sub L. The M sub L numbers the rooms. I need to come up with 3 room numbers because I have 3 orbitals. We said that the room numbers were bounded by L. So it goes from negative L to positive L. So it goes -1, 0, and 1. I placed this electron into the first room, so he gets a +1. And then I need my spin. That electron I placed is going in the down direction, and we said in the earlier video that a down-facing electron is a -1/2. So if I wanted to write these 4 quantum numbers out, the way that we write these out is 4, 1, 1, -1/2. N, L, M sub L, M sub S. So that's just a quantum number review, so I can show you how to use the spin to denote that electron that we're talking about. So let's do the same thing, but let's do it for sodium now. We've already seen sodium. We started this video, what feels like hours ago at this point, talking about sodium. And we said if we wanted to think about sodium's electron configuration, we'd talk about this. If we wanted to talk about the ion, we know that he loses the 3s1 electron. So again, if I had everybody here all lined up, and I use Hund's rule and Aufbau's principle and Pauli exclusion, I could fill them like this. This electron, when I place it right here and it goes in the up direction. Okay? So if I want to come up with a set of quantum numbers for this electron, if you think you've got it, you can pause the video. Write down your 4 numbers that you think it is, and then turn the video back on and see if you got it right. Remember, we want to say N, L, M sub L, M sub S. There's my principal energy quantum number. I'm in my S, so I always have to remind myself it goes S, P, D, F, and that's 0, 1, 2, and 3. These are my L's, right? So my L for S is 0. Because my room, M sub L, is bounded +0 to -0, that's just 0, right? There's no number in between +0 and -0, so he's just 0. And my spin in this case, I've placed him going in the up direction following Hund's rule, and so I know that I have a +1/2. So now we've brought all the skills from Chapter 7 in with the new skills from Chapter 8. We can write electron configurations for ions. We know which electron is being lost, and we know how to assign a full set of quantum numbers to describe that electron. That's the bulk of the weird part of Chapter 8. We're going to talk about periodicity and periodic trends on Thursday. Bring any questions you have from these videos to class. I'll try to have some practice problems for you, and I'll try to email you a practice worksheet with answers provided so that you can work on this over the weekend and you can work on it on Monday and into Tuesday. And I'll see you all on Thursday.